In this video we're going to look at an expression for torsion in terms of the length of the shaft and the angle of twist of the shaft. So we'll begin by considering a shaft, and let's say there's some torque applied. The application of torque means there will be an equal and opposite torque on the other side, and that's going to cause the shaft to twist. So when the shaft twists, our line, which was originally here, has now moved by this distance. And we could put an angular value on that. We're going to call that gamma. So it has moved from here to here by this angle gamma. Now this is very similar to a rectangular piece, and if we apply a shear force to the piece, so if I apply a force in this direction here, the object will deform, and it will take up this shape. So this is our angle gamma here, so we'd say tan of gamma is opposite over adjacent, which is y over x, but the angle is so small that we can just say that gamma is equal to y over x. So that's that area I'm talking about. So gamma is equal to y over x, gamma being in radians. Okay, but if we transfer this triangle over here, we have still got gamma, and now it will be this distance s over L. So y is now s, the length x, here's now the length L. So gamma is equal to s over L. Fine. Now let's look at this circular piece here at the end of the shaft. And we can see that this length s inscribes an angle within the circle. Let's call that angle theta. So this is this piece here. So this is theta. Now for any circle, the circumference is 2 pi times the radius. In this example, instead of using the letter r to denote the radius, we're going to use the letter c. So for this circle, the circumference will be 2 pi c. Now in any circle, we know there are 2 pi radians. So the 2 pi is the angle in radians. So if I just want to look at a small arc length, such as this s value here, then it is the angle in radians multiplied by the radius. So in this case, it is theta times c. So therefore, I can say that this length s is equal to theta times c. But we can rearrange this equation down here to get an expression for s, and we can see that s is equal to gamma times L. That means c times theta must be equal to gamma times L, and we can just rearrange that to put gamma to one side. Now if we were dealing with direct stress and strain, we would get the ratio of stress to strain is equal to Young's modulus. Similarly for shear stress and shear strain, we have the modulus of rigidity, so that's equal to the shear stress over the shear strain gamma. And that's what our gamma is here. This is the shear strain. So I can rearrange that then for a value of gamma. And I now have an expression for gamma, and I can substitute tau over g in for gamma here. So c times theta all over L is equal to tau over g, and now I'm just going to swap the g and the c. So g times theta all over L is equal to tau over c. But we started with this equation, which we looked at in a different video. So I have an expression for tau over c. I now have another expression for tau over c, so I can substitute that in. So this is the equation or equations for torsion, and we'll see how they're applied in another few videos where I'll do some examples.